Let's go. So, hi everybody. Before I introduce myself, just a few words. I'm going to speak about Fedora. So Fedora is a Linux distribution based on RPM, and it has several releases. And the one I've been using during this talk is Rawhide, which basically means the latest version of each packages go into Rawhide, and then they settle down. So it's basically the same as unstable in Debian. Okay, so we're using that as a test bed. All the binary package in Fedora are compiled with GCC, and that's a strong requirement. And basically, we're trying to switch to Clang, not for the distribution, but just to test both the packages and Clang, so that we can gather more information. So that's the overall topic of the talk. So I'm Serge. I'm working for Red Hat as a compiler engineer, mostly on LLVM. And we're going to speak about Clang and Fedora. But before we speak about Fedora, let's speak about Firefox. So this FESCO team stuff is the Fedora Engineering Steering Committee. And whenever you want to do something that does not obey the rule of Fedora, you need to open an issue, and then there is a discussion, and something happens or doesn't happen. And this particular discussion was interesting because Firefox upstream decided not to support GCC anymore as their native compiler, which means that for both OS X, Windows, and Linux, the package is compiled with Clang. There are two main advantages of doing that, which are, if you take apart the quality of Clang, of course, is you only need to support one compiler and not one compiler for Windows, one compiler for OS X, and one compiler for Linux. You've got the same compiler, so whatever compiler-specific stuff you're going to support, it's only going to happen once. So that's cool for them. And the other more technical thing is that Firefox is being partially rewritten in Rust, and the Rust compiler is using LLVM as an internal representation, and Firefox is still using C++. So if both use the same internal representation, it opens a lot of opportunities for optimization at link time, which is not possible if the C++ code is compiled with GCC and the other part is compiled with LLVM. So there are good motivation for Firefox to switch to Clang, but then they still accept GCC fixes. That is, if the Firefox code base does not compile with GCC and you've got a patch, they accept it, but they don't test it anymore. So as a packager, what should you do? Either support the GCC build, which is a lot of effort, or switch to the same compiler as upstream and use Clang, and which is okay because Clang is also packaged in Fedora, but it does not obey the rule of Fedora. So they asked for an exception, and first they got it, and then the exception got removed. And that's the topic of that thread. And why did it get removed? There was quite a lot of objection to using Clang. And without going into the details, some of them were related to the quality of the debug information generated by Clang compared to the debug information generated by GCC, which is a relatively well-known topic. Another one was related to the default flag, like for exception handling, whether asynchronous unwind was activated by default or not for all targets. And GCC and Clang don't have the same behavior to that respect. A more interesting one was the support of semantic interposition. So semantic interposition is an ELF thing that states basically that any symbol that is exported in a shared library may have its behavior or its implementation change at runtime, for instance, through LD preload, which means that it's a strong optimization barrier for any interprocedural optimization. And by default, GCC obeys the ELF rules, and Clang doesn't. Clang did not have any flag to enforce that rule until very recently. And so that's a big difference. It's a big difference for performance. I know that in Fedora, the Python library switched it to no semantic interposition for their GCC build because of the performance impact. But by default, it's not the case in GCC, and Clang has the opposite behavior. So that could be a blocker. A very important topic was security flags. All Fedora packages are compiled by default with a set of optimization flags, and you've got, of course, -02, plus basically most of GCC security features turned on. One of them is Fortify source. It's more for C code, and it was not well respected by Clang. If you activate that, the Clang compiles your code correctly, but the security hardening does not actually happen on all situations, which is a problem. When I'm saying Clang, that's Clang 9, not Clang 10. Someone claims that the stack protection thing were not as evolved in Clang as in GCC. They rightfully pointed out that stack clash protection was not implemented in Clang at all, while it is in GCC. So basically, one of the strong opposition was if you compile your code with Clang, it's less secure, with some definition of secure, than if you compile it with GCC. And that led to Firefox still being supported for GCC by the Fedora guys, which is, from a maintainer point of view, that's not a very good property, but that's how it is. So we told ourselves that's a good opportunity to improve Clang and maybe to remove some of these constraints. So the Fortify, so I had a look to that. And for Fortify, it was very interesting. The way fortification is implemented in the glibc is basically you've got your memcopy, and then if Fortify is activated, you've got an inline definition that overrides the behavior of memcopy. But the Clang behavior was if you use a built-in, and memcopy is considered as a recognized built-in, then you don't care about any overloads that would be given by the user. You're using the actual built-in semantic. And so they were not using the fortified semantic because it was recognized as a built-in. So we changed that, and now when you compile with Clang and Fortify on, and you found a memcopy, if there is an inline definition that changes the behavior of memcopy, Clang is going to honor that version. And so you've got the runtime checks and so on. So that's one more step forward. That's not full Fortify specification. Well, there is no Fortify specification. Right? There is just the GCC implementation, which is tightly linked to the glibc one. But if you want to have the same observable behavior, you're getting closer. So that's one good thing. There's also warnings. At some point, you could say, and many packages do compile with W error, that if GCC detects a security issue and warns about it, maybe Clang should warn about it too. And one of the issues was sprintf. If you can compute statically the size of your buffer, then you can do some kind of checks whether the format is going to fit into the buffer or not. And GCC has some not that much advanced analysis on that topic, and Clang had a few of them, but to a lesser extent. And now Clang implements full understanding of the printf specification and can compute the lower bound of the buffer size requirements and warn you if the buffer is not large enough. So I don't expect that warning to be issued a lot of time, but still that's something that can be now detected. And it has end in Clang, but probably not Clang 10, it will be in Clang 11. And that's something that GCC does not implement now as much. So we are racing each other, but that's saying, no, yeah, that's same emulation, so I'm totally fine with that. About semantic interposition, that sounds like a very difficult thing to implement because it basically means that whenever you've got an interprocedural optimization in Clang, you need to change the behavior of this optimization depending on the status of the symbol based on basically its visibility and linkage type. The good thing was it was already implemented at the LLVM level, but there was no switch to activate that in Clang. So what looked like a tremendous task actually was not that difficult, and which make it possible to land it in 1 week or so. So now the default in Clang 11 is still no semantic interposition, but you can force the flag to -f semantic interposition, then it will be respected just like in GCC for a package where it matters to have symbols change at both load time or runtime. So just to give you an hint about the impact, if you got this small code with semantic interposition on, you can inline foo, but you can't inline bar because bar could be changed at runtime, and so changing its implementation would not have the same impact. If you inline it, then the LD preload thing will not change all the behavior of bar. Then there is stack clash protection. Funnily enough, that's so the stack clash vulnerability is 1.5 years old, and the flag got into GCC relatively quickly and not at all in Clang. The basic idea is whenever you allocate memory on the stack, if it's larger than 1 page, then there is a risk that it overlaps the page guard allocated by the kernel, and so your stack is going to overlap with your heap, which is not a property you want, and that's the beginning of the attack. And so the countermeasure is basically don't allocate large stack, but allocate by chunk of 1 page and touch memory each time you do that, so you're sure that you will trigger the page guard allocated by the kernel, and then you've got your signal and you're safe. So there is an implementation for x86 under review. It turned out to be a bit more difficult than expected, and it's only for x86. It's obviously very architecture dependent. But you can see on that small example that you're allocating a large amount of stack, and instead of having a single sub, you have 2 of them with a move interleaved, which actually touches the page. The good thing with x86 is that whenever you make a function call, you're saving the return address on the stack, so you've got a lot of free probes in the stack, so you can implement that locally at the function level, and it may not be the case of all architecture, which is why it's not implemented at a higher level. So, okay, with that set of patches, most of the points raised during the Firefox stuff got handled, and so maybe the situation can evolve, but it also rings a bell. What about the next package I want to switch to Clang upstream, and what are we going to do? Or maybe we could state it otherwise. We learned a lot by using Clang as a compiler for Firefox within Fedora. Maybe if we don't compile only Firefox but all the package, we can learn much more things. So that's what we did, basically changing the default compiler in a separate build root, so in another Fedora build, and gathering information, and that's the second part of the talk, sharing some of the insight we get. So we're still at the information gathering step, so no answers, but good hints about where we could drive Clang, and that's for real packages. So all the data collection, or the setup of the build route and so on was done by Tom Steller, so huge thanks for him, because I'm not proficient enough on that part. And so he did all the dirty stuff, and I only had to grab full logs, which is totally in my scope, and then starting to implement the thing in LLVM, which I could start to work on. So it's not about Clang, but it's about Fedora. Fedora rawhide requires Python 3. We could still depend on Python 2, but well, the world is moving, so let's move with it. Well, the world started to move 10 years ago, so it's a good time to start to move on our own. Many tools, and I'm not speaking about utility scripts, but tools that the end user actually sees, depend on Python. So that's especially the case for LLDB, for all the debugger scripting parts, but that's also the case for Clang format or Clang format diff. And so if we want to ship these scripts in Fedora, we need to have these scripts run correctly in Python 3. But if you have a look at the requirement for LLVM, it's Python 2.7 still now. So we had to port all the scripts to being portable between Python 2 and Python 3, which was quite a huge task, not a very difficult one, because we are not using a lot of string manipulation in the script, so that was basically okay. But still, it was some kind of an effort. But now all the Python code base of LLVM is compatible with both Python version, and I started a thread which received relatively good feedback that by the end of this year we could probably drop Python 2 and switch to Python 3, which would not be, and Python 2 is not supported for this whole year, so it totally makes sense. And LLVM doesn't have a strong history of supporting aging technologies, so we are upgrading the CMake version quite often, so we can also upgrade the Python version. But at least that was a requirement for Fedora, and this requirement is fulfilled. So another specific tool to Fedora is Anubin. So Anubin, basically, it's a plugin for GCC, and it records all the compiler flags into notes, so that for each function in the binary, we know which compiler flags were used. And that's mostly used for security. You know which security flags were used for each function. And then you know for your whole binary if some functions were not compiled with the appropriate flags. So that's a GCC plugin. And it relies on some specific linker supports. Basically, it was about nodes were attached to function through ELF groups. And when you merge groups, the nodes got removed by LLD. And it's no longer the case, but it was something we needed to implement. And if we want to make one step further, this plugin, this Anubin plugin, could also be implemented for Clang, and that's being done internally at Red Hat by a colleague of mine with my support. So as this plugin is used by default, it was important to do that task. Then about the real normal package, now that we have set up a decent environment, how do you change the underlying compiler? Because we've got all these spec files. The spec file is just a recipe about how you build your actual Fedora package. How do you change from the system compiler to Clang? It turns out that the easiest way to do that was to provide a new set of RPM macro, basically stating that whenever you mention the %cc, it's going to be redirected to Clang, and the same thing for make, CMake, and so on. It assumes that everybody is writing an abstract description of the build process, which was not the case at all. But fixing that is also a way to fix package description. So that was a good road to follow. And once we get at that, we get some builds that fail, we get logs, and we can grab through that to understand why we've got errors. So that's the basic process. And that's the result. So on the 4,000 package we rebuilt, 3/4 of them just rebuilt without any issue, which is both a good surprise, but it also means that 1,000 of them remains. Some of them didn't build with GCC either. I mean, because of some reason which are out of my scope. So we put this one apart. And so we are interested in the 1,141 one that actually failed. And so I had to dig through the error logs and understand why. And so almost 300 of them just failed because they were compiling with Clang, but using some GCC specific flags. And so we get an error. So we also had some Clang specific flags that were added by us in the process, and they were not supported by GCC, which means that our instrumentation of GCC failed, which is also good information to some extent. So stack clash protection is not respected, but we knew that. So some ARM-specific things about neon and quadruple accuracy floats. Something about how you pass arguments, which we could probably ignore in Clang. There's already a bunch of flags that we just ignore, so we could add that one. var tracking is to improve the quality of the debug information, so we can relate that to the quality of debug information in Clang, but we could probably ignore that one too because, well, it's just debug information. It doesn't affect the user experience at all. No trampoline is more related to GCC implementing nested function through trampoline, so it's a way to control that. And no enforce exception and leak specs. It's something to lighten the cost of exceptions or shrink the binary size. So maybe we could implement that. I don't know. Sometimes we just fail to hook Clang and instead of GCC, and we detected that. So to detect that, we just go through all the binaries generated shipped in the package, and we go into the command section of the binary, and if we don't find compiled with Clang, then it means that we did not compile any object. If we find compiled with Clang, it means that at least one object of the package got compiled with Clang, which is not all of them. There is always, unfortunately, the GCC, unfortunately for our tracking thing, the GCC comment, because we are still using the CRT stuff and GCC as a linker. So there is always the GCC watermark. But at least some of them were not compiled at all, so we need to understand why. Some people find it smart to compile with W error, and for our task, it's not smart at all because Clang and GCC differ a lot to the extent of the warning implemented and what kind of error of situation they catch. And so something like printf being redefined is not an error on GCC, and it is, it's not a warning on GCC, but it is in Clang. Ignoring return value, detective infinite recursions, this kind of thing. So it's probably, we're not going to implement the same set of warnings. So I don't quite know what to do about that one. Probably remove W error would be a decent approach. But I'm not going to spend much time on that. When you activate fastmat, you've got some specific implementation of the mat library. And it turns out that GCC relies on some new symbols that's finished by finite. And these symbols, sometimes we fail to link with them when using Clang. I can't say why. But so it could either be a packaging issue or a Clang issue, I don't know. But still, it means that there is some implicit things are coded in GCC or in the package that are not well described. The famous configure error. We have got a lot of them. You may be aware of the difficulty of writing portable autoconf tests. And if you're not, having a look at all the tests that fail because Clang is not capable of compiling a C code. That's the only output we get from the configure. We could, of course, have a look to the config.log. But so many packages failed just to configure because using Clang during the configuration step just fails. My hint about that is that because we use some specific compiler flags, they are used during the configuration step. And so if we've got any of these W error things or unsupported argument thing, we're going to detect that at configuration step, and so we just fail to configure. Does it mean that we need to rewrite the configure step, which means contacting each upstream package to update that, or do something else? I can't tell, but that's something which will not be very pleasant to fix, and maybe not of much interest with respect to just Clang. Something that is important for Clang, but only in Fedora, sometimes Clang fails to find some part of the runtime, either because it's not well packaged or because there are some assumptions that are not met. I am doing the packaging, so I do hope that it's not a packaging issue, but I fear it is, and we need to check that. I can't tell about the GCC_C, and I did not took time to investigate what this implement, but we can discuss about it a bit later. Sometimes there's disagreement on the standard. So that's something that is very valuable either for Clang if they wrongly disagree, or for the upstream package if it means that they could improve their code base. So sometimes it's linked to GCC extension, so the one like you don't support a nested function. Sometimes it's comparison between pointers should be equal or different, but not ordered comparison. And I don't know what the standard actually says about that, but obviously GCC and Clang disagree. So maybe we could improve the situation. And sometimes there is just use of undeclared identifier, and I will be surprised to investigate and check why Clang doesn't find the identifier while GCC does. So that's more of an upstream issue. So the language extension stuff. Here you have a nested function, something you can easily write with a lambda in C++, but GCC allows to do that in C through an extension, and some package rely on that. And it's probably going to be difficult to make them change their mind, because if they choose that extension, it's because it makes their development flow easier, or I don't know. And when you try to compile that code, there is a warning like, okay, Clang is not supporting that, and it's not going to support that. So it's clearly stating in the error message that we can't do anything about that. Or we could maintain a patch at the Fedora level, but I don't want to do that. OpenMP, and it's also related. It's probably related to either packaging issue or dependency issues. Sometimes Clang doesn't find the runtime support for OpenMP, or the configuration step fails to detect OpenMP when compiled with Clang. We need to investigate, because that's not a good thing if Clang users can't use OpenMP out of the box in Fedora. That's probably not a Clang issue, more probably either a configuration issue or a packaging issue. And some packages just still use GCC because their hardcodes make, or they hardcode GCC or G++, either in the package or in the actual upstream sources, which makes sense because if you're not sensible to portability, you just use GCC and it works. And there's no reason to worry about that until you realize that some users may want to compile with Clang with good argument, or Clang or whatever. It could be Intel compiler because of performance, I don't know. And then it could be an improvement both for the packager and for upstream to have a more generic build process. So that's the end of my talk. The ideas I would like to share, I'd like to share with that talk was there's a lot of things to learn while having such a diverse set of programs to compile with Clang, and that's far from the test suite of LLVM. So a good opportunity to improve, probably making all this information available in a way that anybody could access them, opening all the bugs on Bugzilla or on GitHub, depending on how it evolves, could be a good thing. It's probably less important for the LLVM community to do the upstream work. I mean, trying to update every package packaged in Fedora to support Clang is more of a social task than of an engineering task, so it requires special skills. But some people may be open to that and some may not. But that's still an opportunity for upstream to improve too. But I see a lot of good things for Clang, at least for the past months when I've been working on that. And so it also fills my daily job on interesting tasks. So on a personal point, that's a good thing. And I wanted to last with that final error. So if you are compiling in C++ and you name one of your member function dprintf, and then you compile with 45 source, but you order your includes in a way that sometimes you will get the macro redefinition from the stdio headers, and sometimes you don't. Then you end up with part of your class having a dprintf member and the actual implementation using another name. And so you've got an error just because of basically macros and the way they interact with 45 source. And that was a funny one. Only one in the whole Fedora code base, but an unexpected one. So now if you have any question, I'm happy to share more information. Or yep.
Thanks for your talk. I was curious about, you mentioned earlier a GCC plugin about recording the exact compiler invocation in the notes section of the ELF object. That sounds generically useful. Theoretically, that could be a -f flag in the compiler and doesn't need to be a plugin, right?
So the question was, recording all the optimization flag and security flags is something that is generally useful. And so why using a plugin and not an actual compiler flag? Maybe, I'm not the one developing that plugin. The plugin is open, so that's not a proprietary reason, but that could be. My guess would be it's easier to write a plugin. It's maybe the first step before you go into the code base. That's how academics do. They don't write into the LLVM code base. They first write plugins, and eventually it gets in. So a plugin is a good first step. So that could be an engineering answer would be, why not starting with a plugin? It's easier. You can maintain it. You don't have to get through the review process of the actual compiler. And should it evolve into an actual compiler flag, it does make sense, to me at least. Yeah, whatever order.
Thank you for the interesting talk and many interesting details. Let me wonder, do you consider this journey a success for you? And also, like, as you still got a lot accomplished, what are the most valuable outcomes which you got for your day-to-day work out of this project?
The question is
for testing, but for testing Fedora. But what kind of testing could you elaborate? You get out of this reporting?
I don't quite understand the question. Can you repeat, please?
You said you did this project for testing.
Yeah.
Testing what? Can you give more details? What you tried to test with this?
Mm-hmm. So the question is, we did that for testing. What's next, and what are the conclusion or the outcomes? And so my personal take on that is Clang LLVM did improve a lot thanks to this testing, only on the Firefox part. And so from all the information we gathered on the larger scale tests, there's a lot of situations where we could improve Clang based on the GCC experience, basically. And that's a good thing. I mean, it's not only about trying to match GCC. So that's the initial motivation, but in the end, what you get is more feature for the Clang users. And I'm going to go on that way, because not for all the flags, I'm going to sort out the things that I'm interested in and the things that seems valuable for Clang as a whole, or could be accepted, because like nested function, I could find it interesting on my own, but it won't get accepted upstream, so I won't work on that. And it also provides opportunities for people to work on that apart from just the LLVM team in Red Hat. So basically, it provides more opportunity to fix bugs or add new features, and driven by actual test case and not only my imagination. Victor?
I know that the FreeBSD operating system is fully built by Clang, and there is also a project to rebuild Debian using Clang.
Yep.
Are you collaborating with this project?
I'm collaborating with the Debian project on that. So the question was, there's not only Fedora, BSD systems, some of them are compiling with Clang. There is a side project of Debian, of recompiling Debian with Clang, which has much more history than we have. Are we in our bubble or collaborating? So it happens that I personally know the guy in charge of that for Debian, and so we do collaborate both on the packaging side. Whenever I have a patch that I need to apply to LLVM, I'm discussing with him, are you applying that patch in Debian 2? Why for this kind of thing? And also for the general approach, especially for Firefox, because this guy appears to also be in the Firefox team. So, for instance, all the Fortify stuff and the stack clash protection stuff, while being reviewed by LLVM, were also tested on the Firefox version, recompiled, because they plan to use it. They are really interested in that feature. So even if they don't make it to the Fedora build, they will make it to the Firefox build. So there is some kind of cooperation.
One more question, I think.
Yeah.
What about actual testing? You're just testing that it builds.
No. It pains me that you have so less trust into the packager job. Whenever you do a package, you've got a test section, and basically you're running the tests.
An empty test section.
No, it's.
How many packages actually have tests?
So I can only speak about the package I maintain in Fedora, which is very small amounts, but all of them do have a test section. So it's also true that for some architectures, the test section of LLVM has a if arm, then okay. But well, we're actually running the test and ignoring the results, but not for x86. So, but there is a test section, and we are encouraged to use it. And I think some, I've not mentioned that, but some of them we had segfault in the test. Like the tests were run, and the segfault. And from my experience on working on obfuscating compiler, we don't like debugging this situation because you don't know the test, you don't know the actual program, and that's a pain. But that's one thing that could be very interesting, because if Clang is miscompiling something,
it's a next logical step after
yeah.
building the packages.
Okay, I think we better stop there, but thanks very much.